Am I the last? Am I the last speaker?
Yes. Well, the last lecture there is a speaker at 4.
Ah, that's true.
There is a.
But that's not part of the official. Is it part of the official school? Well, I'll thank the organizers anyway. It's fine. You'll get 2 thanks. It's it's always the duty of the last speaker to thank the organizers.
We appreciate it.
No, I didn't run out, but I wanted to gift you immediately some. Then I'll send you a box. But
Certo. Vamos começar. Oh, in English. We're starting then the last lecture. Pietro is giving his last lecture on black hole thermodynamics. Thank you.
thank you. So, as the last speaker of the school, it's my honor to thank the organizers for organizing the school. It's been great for me. I hope it's been great for you too. Thank you. Well done. Okay, so what have we done in the first 3 lectures? And then we'll see what we can do. So in the first couple of lectures, we showed that if you have a Lorentzian spacetime with a killing vector, that has a non-constant norm. In particular, if this killing vector has a null hypersurface to which is also normal, then this null hypersurface is called a killing horizon. And associated with this killing horizon, we can define a concept of a surface gravity. And we introduced a physical meaning for the surface gravity by normalizing the killing vector such that its norm is -1, its length is -1 at infinity, and said that an observer along a orbit of Xi would observe a temperature that is proportional to the surface gravity, Associated to this, we said that the main example of this type of space-time are black holes. And for black holes, there is, the killing horizon has a bifurcation surface. there is a codimension 2 surface inside space-time where Xi vanishes to Kur, and the area of the bifurcation surface behaved like an entropy, in the sense that in any non-stationary process that changed the black hole background, the area is non-decreasing, and moreover, it appears in the first law of black hole mechanics associated with the scaling horizon exactly in the way that an entropy would be. That is, it's dual to the temperature. Okay, then I argued, without any particular, that in Euclidean spacetime there is a natural dual to these statements, in the sense that there is always a connection between a thermal Lorentzian background and a Euclidean background via the KMS condition, which says that the correlation functions are in thermal Lorentzian are periodic in a particular sense, in the sense that they switch also the order, with period beta are periodic in imaginary time with t plus I beta, roughly, with Te plus beta, where Te is It. And then we said, this looks like we can move to the geometry. We can just move the entire problem to geometry. That is, we can do this Wick rotation, and if we do this Wick rotation, we cut off the space-time, in the sense that we never go beyond the killing horizon. The bifurcation surface the bifurcation surface becomes an S2 or a sigma, if you remember in James's talk yesterday, over the origin of a disk where Te is the angle. The angle. And moreover, we argued that the identification of the periodicity in the KMS formulation was related to the smoothness of the background in Euclidean signature, in the sense that to avoid conical singularities, if and only if Te following this prescription, so following this, we introduced the idea that the partition function of gravity was the integral over all the metrics filling a certain boundary. And in particular, we argued that in the semi-classical approximation, that is h bar to 0, then the leading term in this expansion is just the on-shell action of a solution of the equation of motion. Using this approach for boundaries that were S1 times S2, we found the on-shell action of two spacetimes, thermal ADS and ADS Schwarzschild. that are both static and spherically symmetric. We computed these actions, and we found that first we showed that in both cases, well, in particular in the black hole, we can indeed use the quantum statistical relation in the sense that the action was related to the energy and the entropy in the same way as should be the free energy of a thermal system. But also we showed that there is a phase transition at a temperature called the Hawking-Page temperature from the paper by Hawking and Page that is proportional to 1 over L. But in fact it's equal to, between thermal ADS and the black hole. Okay, this looked all nice and all smooth in the sense that this gave us some confidence that we can indeed believe this method, we can trust this method because we reproduced using this Euclidean prescription, that is that we need to sum over smooth spacetimes and we can really take their on-shell action as the free energy, and we can recover from smoothness the temperature associated to the actual horizon, and by really believing that this is the free energy, we can recover both the energy and the entropy that appear also in the Lorentzian configuration. Okay. Any questions on what I said until now? Yes?
So there's a problem when you perform acting that goes for A fields that I think will happen there too. Because there's a redundancy in the
Yes, that's very true. Yes.
the techniques that you
Yes.
was taken into account.
Yes. Yeah. Yes. And that's in 10 minutes. Any questions on this understanding, on this consistent picture? Okay. If not, let's move to the problems with this picture. This was the picture, I would say, in the 80s. This is well, if you included the SFT picture, something like that. This paper by Hawking and Page is from '82, and everything was consistent. Fun fact, fun sociological fact. This paper was written in '82. Until 1998, it had, if I'm not wrong, 17 citations. Between '98 and 2025, it grew up to, I think, in the 6,000 citations. So, you know, never lose hope. Because at the time it was just a game for thermodynamics in the sense that it works if you put gravity in a box. But with the SCFT, this becomes, the Hawking-Page transition really becomes a confinement-deconfinement transition in the dual gauge theory phase. Okay, that being said, the gravitational path integral is still the subject of research, of current research. Because there are many, and every year there are many papers written on the formulation of the gravitational path integral with or without supersymmetry. Because there are many issues with this prescription, if we really believe this prescription. So I will not be able to tell you everything about all the subtleties that appear here, because I'm not even an expert in all of them. But I will tell you some things that are interesting and that emerged from questions that I received in the previous days. In particular, I plan to tell you about what happens if the spacetime is non-static. I wanted to also tell you, to connect with James's talk and the Wall's idea for how to recover entropy from topology. And then I will flash subtleties. In particular, I will discuss, what do I want to discuss? I want to discuss topologies conformal rescaling, and gauge redundancies. Because most of them have been, people have asked about these things, so it's worth discussing them. Okay. So, until now, I've only worked with static spacetimes, so spacetimes where there was a globally defined killing vector field. That is also hypersurface orthogonal. Now, I'd like to relax a little bit this assumption, and I'd like to consider a stationary spacetime. In particular, I'd like to consider a spacetime where there is rotation, where there is a space-like rotation as well. So it's stationary and axisymmetric, formally. So stationary because there is a globally defined time-like killing vector, which I'll call K. But it's also axisymmetric in the sense that there exists another killing vector that is space-like, that I call MA, that generates a U1 in some, at infinity at least. Okay? So I can always construct adapted coordinates with this, to these killing vectors. So I'll construct time, and I'll construct an azimuthal coordinate phi associated with this vector. I claim that this is the generator of the angular velocity, or the angular momentum, in the sense that if I construct where omega is just a factor, then I can identify this for a black hole with, for a black hole, omega is angular velocity of the horizon. Why do I do this? I construct adapted coordinates, then V is simply dt plus omega d phi. I take an orbit of this, then modulo a constant, phi uguale omega t. So this is really the angular velocity of the spacetime. And in particular, if I take V to be the generator of the horizon, so to be the killing vector that vanishes at the horizon, then this is identified as the angular velocity of the horizon itself, of an observer that rotates at the horizon. As a matter of fact, I don't just include stationary and axisymmetric, I also want to include charge. Until now, I've never considered the Maxwell field, but I want to add the Maxwell field. So if I assume that the boundary is again S1 times S2, then how do I define the configuration of the Maxwell field in the spacetime? I need to do some gauge invariant statement. So I can only fix the holonomy around the S1. So the holonomy is exp which, if this has period beta, is just E beta times phi, provided A is a provided A is a constant, I can always define this phi. This phi, in a sense, is the electrostatic potential. In a sense that will become clear in some minutes. Okay, but beta phi is the holonomy of the gauge field around the S1. You'll immediately notice that something is wrong. So this object phi is real if and only if A along TE is real as well. But this means that AT is pure imaginary. Well, okay, it's pure imaginary. But this doesn't seem consistent because I would like to start with spacetimes that in Lorentzian signature are really well defined, are really real. So we find that there is already something wrong here, something to think about here. But this becomes much more involved once we add an angular velocity, because an angular velocity is associated, as we will see in a second, with a cross term. So the existence of the angular velocity is associated with a cross term g, t, xi, where xi are the other coordinates along the hypersurface. This is by definition, in the sense that if it's not hypersurface orthogonal, then it has a projection on the hypersurface, which is this cross term. If this is non-zero, and it's real in Lorentzian, then in Euclidean it will become complex, it will become pure imaginary. Therefore, the entire metric that I need to sum over in the gravitational path integral is complex. But I've never given you a recipe on what to do with a complex metric. What's a smooth complex metric on a manifold? It's a weird statement. It's a well-defined statement, but it's a strange statement to consider. Okay, so I'll tell you what happens, and there are no answers, so I can only tell you the problem. So I'll formalize the problem a little bit in the sense that I'll show you how to generalize the KMS condition with angular velocity and charge. So if you have angular velocity and charge, then you need to generalize the Gibbs ensemble. And then you say that the operator in the grand canonical ensemble, the VEV of the operator in the grand canonical ensemble, phi q minus omega j. And the density matrix is e to the minus beta h minus phi q minus omega j. This is the definition of the grand canonical ensemble, nothing fancy so far. Now I consider the Whiteman functions, so the correlators, of a scalar field, a complex scalar field, phi, which depends on t, a coordinate phi, notice the difference between the phis, sorry, and a bunch of other coordinates. If you remember, 2 days ago, there was no phi, I had tx underscore, and these were d minus 1 coordinates. These are just d minus 2 coordinates. They could be, for example, the radius and the other angle in the 2-sphere. Q and J, so the conserved charges, are upgraded to operators that act in the Heisenberg picture on the scalar field in the same way they act from Peskin, in the sense that this just multiplies it by the eigenvalue, the charge of the field, and the angular momentum. Let's use alpha. Let's keep omega for the angular velocity. This changes the angle, rotates the field. This is just the action on the fields in the Heisenberg picture. Now I need to generalize the KMS condition, so I need to consider the Whiteman function in presence of a beta, but now also in presence of a phi and omega, t phi xy, which is by definition z to the minus 1 trace of phi tx phi 0 y e to the minus beta minus equal phi q. This is just a generalization of what I had the other day to complex and the inclusion of these two. If you do the same cyclicity of the trace definitions and you act with omega and j, then at the end of the day you'll show that this is t plus I beta, phi plus I beta omega, x, y. So I have exchanged phi dagger and phi, acting with this and introducing a resolution of the identity here. And then I have recognized the Whiteman function in the opposite order, but evaluated at a different point in space-time. Well, in the analytic continuation of space-time. So this part is the same thing that I had as KMS condition there. In this part, instead, is new. It says that the coordinates are twisted when I have to do the identification. So in Euclidean, where I put inverted commas in Euclidean because it's not Euclidean, it's not even Riemannian. Well, it's the same thing, but there is a twisted identification. In the sense that TE and phi should be identified first with the canonical azimuthal periodicity, in the sense that if I only go around the two spheres, then I'll identify the same points. But if I go around the circle on top of the two spheres, there is a twist, in the sense that as I go around the circle, I also need to go around the two spheres, where omega is I omega. And I've introduced this analytic continuation because otherwise I don't know what I'm talking about when I say that an angle identifies with an imaginary term. Okay? However, I can still close my eyes, well, keep my eyes shut, and just go and follow my nose. So, if I follow the GPI prescription, so the gravitational path integral prescription, then computing the on-shell action of the resulting geometry, which depends on beta, omega, and phi, will give me beta times the free energy in the grand canonical ensemble. Okay? I'm just following my nose. Okay, so in light of time and in the fact that it's better to have lunch than to see line elements that are one blackboard long, and the entire thing is in my lecture notes, I'll tell you that there exists a space-time feeling with holonomy fixed and twisted identifications. It's called ADS Kerr-Newman. You'll notice that the poor people who found all the ADS solutions associated with the flat space ones didn't get the chance to name them after themselves. There's Kerr-Newman, and some guy, Carter, wrote a long paper explaining how to get the ADS, but it's still called ADS Kerr-Newman and not the Carter black hole. Anyway, so you can compute the action of this. Okay, so we need to use the gravitational path integral prescription. The metric of ADS, the metric and gauge field of ADS Kerr-Newman are real in Lorentzian and include and contain ds squared, contains a long term, but it contains a term that is h t phi dt d phi, well, g. And also A contains a term that is q r something, a function dt minus a square of theta d phi. And this term is proportional to a times well, a is just a parameter. So the entire thing, the entire metric, depends on three parameters, m, a, and q, which are the mass, which correspond, in some sense, to mass, angular momentum, and electric charge of the solution. You'll see that as soon as I do the Wick rotation and I try to do that path integral prescription, the metric becomes complex. Because the metric tensor is complex, because when I take dt to minus it, then this object becomes pure imaginary, but the others remain real. And the gauge field is also complex, because this term becomes complex, and this remains real, becomes pure imaginary, and this remains real. So I don't know what to do. However, I can do an analytic continuation of the parameter. And define A equals to I alpha and Q equals to IQ. Doing this leads to a real metric and a real gauge field, right? Because I take t into minus it, this picks up an imaginary unit, then the unit I goes outside, Q is also been analytically continued to imaginary, so this becomes real, and same thing for the cross terms, for the shift vectors. A becomes pure imaginary, T becomes pure imaginary, the entire things remain real. Now I am back in the family where I could do the entire gravitational path integral prescription. So now I can use holographic renormalization to compute the on-shell action. Sorry. I can't do this until I check smoothness. So now I have a real metric and a real gauge field. I should check smoothness. We should give me beta, and it will also give me omega, because when I go near the horizon, the would-be horizon in Lorentzian, I need to identify, it turns out that I need to identify T with a beta and phi with a certain omega. So there is a twisted identification also due to smoothness. And also for the gauge field, requiring that the gauge field is smooth everywhere, so that is globally defined even at the point at the origin of the cigar, leads to a choice of gauge. Such that holonomy at infinity is equal to the prescribed one. So this is indeed the right space-time that fills the boundary condition that we have. We can compute, now we can use holographic renormalization to compute the action, and we can check that the action satisfies the quantum statistical relation, let's call it E, minus phi sum QE minus omega sum J, for some values of Q and J that are given by some ADM-like formalism, a Komar-like formalism from ADS. Therefore, I identify S with the entropy, with the thermal entropy. And what is S? I've not told you, but the S that appears here is the area of the horizon, is the area of the non-round two-sphere over the origin of the cigar that I had included here. So S area of the horizon is really the thermal entropy in the sense that it's the thing that I identify here. Not only that, beta that I computed out of smoothness is indeed the inverse of the surface gravity that I can compute for the Killing horizon of the Lorentzian ADS Kerr-Newman. So everything works. You can really see this expression as a Legendre transform from the grand canonical ensemble to the microcanonical ensemble, where you have S as the function of as the state function. However, there is a problem. There is a big problem, because when I did this, I did an analytic continuation. I can do it here. When I did the analytic continuation of the parameters, I also, out of definition, did an analytic continuation of the Lorentzian electrostatic potential and angular velocity. Therefore, effectively, now in Lorentzian, the thermal density matrix that I'm measuring, that I'm supposed to be considering, it's not real, but rather it's become this object here. This is not a well-defined operator. So this analytic continuation that allowed the gravitational path integral to make sense in the same sense as it did yesterday led to a Lorentzian picture that is instead nonsensical. So you have the problem, what am I integrating, what am I doing with this integral? However, it works. We don't know why, but it works. So there is some research on this currently happening. You should have good reasons to believe this operator. One of the good reasons to believe this operator is that it makes the space-time supersymmetric, so it's a sensible thing to do, including complex metrics. Okay. Issue 1 presented. Questions? This will be a flash of issues. I don't have a consistent story. It's just a lot of issues that appear. Yes.
No, it's more a comment than a question, which is just you can do real integrals by saddle point methods.
Yes.
And it's not uncommon that the dominant saddle point is complex. We can do this very elementary with just a real integral. And it has to do with deforming the real contour of the complex sense. So none of this was suspicious or worried from that perspective. Doing a saddle point method, you expect to have to deform in a complex way to get complex things.
Yes, so from the GPI viewpoint, there is no issue. The problem is, what do you make of this operator? Because in order to work with the complex metric, to avoid working with the complex metric, you had to analytically continue the parameters. And then as you look back, don't know what you've done. I don't know. Yes?
So the area is really of the horizon this sphere is seen that it's also some important part of the space. Because in relating to the curved space, you have the horizon, and this sphere also a special part of the space time. Is it somehow seen in this picture?
So here,
It's actually about the growth process in which is important part of space. Somehow
no, so here it's, I guess it's the area of the ergosphere in the sense that I am Vic rotating and then I'm capping off the space-time at the largest root of the space. So of the function defining the space. So it's really where the generator of the horizon becomes null in the first point. No, in the Euclidean approach, I don't know what's the role of the ergosphere. Is it?
It's asking the ergosphere is outside the horizon.
Yes.
It's a region that's outside of that. So you're just asking, does that contribute to the thermodynamics? I don't know, but I don't.
No. Well, one thing that you can wonder is whether there is some bound on omega such that this operator all of a sudden becomes well defined. And there is. So in ADS, you can show that there is a natural bound on omega, and the operator becomes bounded. So there is a good idea for what to make of this operator.
But that operator, is it like, even about ADS, like, when we have German solution, I mean, to avoid the main singularity, I think we have the bound from ADS. I mean, if I go to this dimensional A parameter of the rotation of the black box,
Yes.
it should be between 0 and 1. And
Yes.
if that also your variable omega cannot be arbitrary high.
Yes, so this is the same bound that you obtain from that Euclidean bound corresponds to the superradiance bound that you would find in Lorentzian, which is this omega less than 1.
But in the Euclidean estimated version, like in Lorentzian, we say we want to avoid named singularity.
Or superradiance, I think more properly.
In Euclidean, you have some reformation of that, like what you want to avoid. I mean, is it something geometrically?
Oh, well, the metric diverges when omega is 1. One of the metric components is degenerate.
Even if it is above 1.
No, so you start from 0 to 1, and then at 1, the metric just doesn't exist.
But for values bigger than 1?
Oh, so in the disconnected component, so this is really disconnected from Schwarzschild, like you can never get back to Schwarzschild.
Like physical continuous process, you cannot get that, but
I don't know. It's a solution to the Einstein's equation. It's not, in Lorentzian signature, the metric that you're describing is not Lorentzian. It has minus, minus, plus, plus signature. Because you have flipped, if you are above 1, then you have flipped also the sign of one of the two. So it's, I'm not sure it's
I mean, it's not entirely Euclidean, but it's even worse Lorentzian.
yeah, so it's Lorentzian after the Wick rotation. Yeah, I don't know. Yeah, I have nothing to say, meaningful to say. Okay, so you see that these are fun issues to think of. So the next comment that I wanted to make is related to our first law, to the formulation of the first law that I mentioned at the beginning in the first lecture, and the appearance of equivariant localization that was the subject of James' talk yesterday, which is the idea of entropy from topology, in a sense. Okay, so now I'll not give the entire description of the most general space-time, because that's very difficult and still, very much work in progress. But there is a cute picture that you can derive. So in all the thermal cases, there exists a symmetry of the solution in the sense that it's both an isometry, but it's also a symmetry of all the other matter fields that you can have. It generates really a symmetry of the entire solution. The idea is that there exists in the space-time this symmetry has closed orbits with period beta, with length beta. So there is an S1 vibration over your space-time. When we want to compute the entropy out of the space-time, out of any space-time, we compute the energy, we compute the on-shell action, and then the statement from thermal field theory is that the entropy is beta squared times the second derivative of the free energy, the first derivative of the free energy, but the free energy is I divided by beta, and therefore it's this operator applied to the on-shell action. Now there are two cases, there are two obvious cases. Case one, the symmetry acts freely. Which means that there are no fixed sets. There is no point that is not moved by the symmetry. This is precisely the case that was not treated in James's talk yesterday, because then the method doesn't work simply, or it gives 0. If the symmetry acts freely, so if you have a group action that acts freely, then you can construct the quotient everywhere, and this is a well-defined manifold. So I can compute the on-shell action, which is an integral over m of some form that represents the Lagrangian of my theory, splitting the integral as first an integral on the fiber, and an integral over the base of this trivial vibration. But this is beta times the integral over of L prime, simply because L is symmetric under the action of my symmetry. Therefore, it doesn't depend on any of the adapted coordinate that you construct along C, and therefore this just gives you a factor of beta. This means that every time the action acts freely, there is no entropy. Because anytime the on-shell action is linear in beta, this operator kills it. Okay? So all the space-time that have an action that acts freely possess no entropy. And this is a powerful statement, because I'm only talking about group actions and topology. There is no... I didn't tell you about the physics on the space-time. So if you tell me that you have a space such as thermal ADS that has this topology, it's S1 times R3, then I already know that this has vanishing entropy. Then there is the more interesting case where the symmetry has some fixed points. So these are sets where the Xi vanishes, and therefore there is no action on these points. They are fixed points, like the poles of the S2. When this happens, I cannot construct a vibration, a quotient. Instead, I have to take out the set where the symmetry, where the fixed point, where I have the fixed set. So I have to take m minus the fixed set, and then I can construct the quotient. Or, more properly, in order to reconstruct the entire integral, I surround the fixed point set by a tubular neighborhood of radius epsilon. So I surround them with some, let me give you a concrete example. A concrete example of this case is are the black holes that we studied until now. Parentheses. Basically what I'm doing now is proving the fixed point BVAB theorem that James invoked yesterday at some point. You'll see that this is precisely the proof. That's not really true, but you know, it's an application. In this case, the symmetry that we were talking about here, the thermal symmetry, blah, blah, rotated the R2, the cigar factor, and had a fixed point at the origin. At the origin, I cannot write this as an S1 trivial vibration, right? Everywhere else I can. If I add S1 times R, I would be able to. But at the origin, this vibration degenerates. So I have my cigar. Over all points of the cigar, I have an S2. And what do I do? So this is a cigar. It's a three-dimensional object. Well, you understand what I mean. Where my Killing vector acts like a rotation. This is the fixed point. I surround the fixed point with some neighborhood of radius epsilon, and everywhere else I have just a cylinder, so I can just take the quotient. So I can take m minus m epsilon over S1, and this is a well-defined manifold that I call B, the base of my space. It's B is this one here. Here, I was not able to do it. Remember this. But as I take epsilon to 0, then I recover the entire integral, because it's a continuous process. What's fun is that the integral that I have to do here, which is minus 1 over 16 pi r plus 6 divided by L squared vol, on shell becomes 1 over 16 pi. On shell, r is minus 12 divided by L squared, so there is a minus, so it's 6 divided by L squared vol. Let's remove the factor of 2. And then, it's an amazing fact that depends on the existence of a Killing vector lemma, that for all isometry, you can say that this holds. So, Xi, my Killing vector, contracted in the volume, is exact. Xi is a global form. This was precisely phi 2, in yesterday's James talk. Right? So this is Xi in phi 4 equals d phi 2. So it's precisely the beginning of an equivariant form. However, so in principle, I would like to go to phi 0, but I don't have to, because in this case, I can just limit myself to phi 2. Why? Because now the integral over L, the integral of L over the entire space, remember that this, on this space, I can do the same procedure that I did here, because on this space it acts freely. So I can just do the integral over the S1, well, let's keep the, over B, which depends on epsilon, right? So it's B epsilon, over B of what? Of -1/2 d star dxb. But now I have an integral over a three-dimensional space with a boundary here of an exact form. I can use Stokes' theorem, and this is just the integral over the boundary of -1/2 star dxb. But this is the integral over phi 2. In the epsilon to 0 limit, this is kind of true, this becomes, it's not true, but the idea is that this becomes the integral over the bolt of phi 2, which is the first term in the fixed point in the BVAB theorem. This is the way you prove it. You show that you construct this everywhere you don't have a fixed point. The action acts freely, so you can do the fiber integral. But then you obtain an exact form. Then you apply Stokes' theorem. You'll get a contribution from the tubular neighborhood surrounding this, and you'll just get the integral from the bolt. In this particular case, you can show that what time? How much time do I have? Yeah, here I can even tell you why you get exactly Hawking's idea. So dxc is the infinitesimal action of xi, is the weight part. It's the thing that yesterday was with weight. So on the tangent space to the bolt, so on the tangent space to the S2, xi acts trivially. There is no infinitesimal action. Everywhere else, it acts like a rotation on the normal plane with a weight that yesterday was called B, and that I called the surface gravity because I came from Lorentzian, but that's the same idea. So you see that this is dxc. Then you can take the star of this, you'll get that it acts on the tangent space because of star of doing the Hodge dual. So now the star of this acts in the opposite. Sorry, I used to go mad when people did this on the board of erasing something and all of a sudden it's the same formula. But now I understand why they do it. So now star of dxc is an integral on the tangent space to the fixed point, so on the bolt. In particular, once I recall that the volume of the tangent space is just epsilon 1, 2, right, is a E1, 2, so it is just proportional to kappa vol. But now, if you are careful, and you remember that beta is inversely proportional to the surface gravity, and you do you keep all the coefficients, you'll find that the integral of this object is precisely the area of the black hole horizon, minus. And then, when you apply the formula, you'll find that the entropy minus the action, but the action is minus the area of the horizon, and you have proved the Bekenstein-Hawking argument. Without any metric. This was the power of what James was saying yesterday. However, here I had to cheat you, like badly. I did a bad thing. Okay, I will not ask you why, but I was only worried about this boundary. What I did not tell you, but you should have complained, is that there is also, this space is non-compact. There is a boundary at infinity. And I did not tell you how I regulated that. I told you, the on-shell action is just the area of the black hole horizon, that's the entropy, puff, puff. But that's not true. This is plus divergent from the opposite boundary, which is the other boundary there. With supersymmetry and a lot of computations, we showed that this divergent part is 0. and you do indeed get the fixed point formula. So the on-shell action is only fixed point terms. Okay. Questions? As you could see, I'm very excited about this work. Questions about, yes? No, it doesn't make you avoid the divergences. What the supersymmetry does is that it tells you that, so now I'm just repeating what was said yesterday, sorry, but what the supersymmetry does is that it guarantees you that there is an isometry without having any assumption here. So all the supersymmetric spaces have an isometry that is created by the bilinears that were yesterday. Moreover, there is an ambiguity in the forms, right? Because, again, I cheated you a little bit, because I told you that it's this, and then I integrated, and I obtained this. But that's not true, right? I could have added any other two form that was closed. And this would have screwed up the result. It wouldn't have screwed up the integral, because you can add and subtract the same object to the two sides. But it would have screwed up the fact that, it's only fixed points that contribute. With supersymmetry, you can fix these ambiguities. There is a canonical way of saying these ambiguities do not appear, which are the forms that James wrote yesterday, so the ones that depended on the bilinears. With those forms, there are no ambiguities. Other questions? Okay. For YouTube, these are unpublished things. Don't steal. Okay. So this was not really an issue, but it was a feature of the Euclidean method. So let me return to the issues. The other issue that I said I would talk about, because I'm going to go through them relatively fast, because I have nothing to say about them, apart from the fact that they exist. So the first thing is the topology, I think, yes. So it's the multiple topologies. This is it's just a truism. There is not much to say, in the sense that there are many more Riemannian manifolds than Lorentzian manifolds, because there's a theorem that says that for any manifold, so for any topological space that is Hausdorff power compact, and you can create a diffeomorphism structure on it, there exists a Riemannian metric. That's not true in Lorentzian. You cannot construct a Lorentzian metric that is everywhere defined on the two-sphere or on the three-sphere. In order to have a Lorentzian manifold, you need a special direction. So you need a special killing vector, well, not killing, a special vector field that is everywhere defined and has a consistent, if you want it future directed too, and has a consistent orientation and direction. So the Euclidean quantum gravity, so the idea that I should sum over all the topologies that fill a particular boundary includes many more solutions that are not Lorentzian. That's it. You can construct many Euclidean instantons, so-called instantons, so solutions to the Einstein equations that have a metric and have a finite energy. So they are good solutions in the sense that there is nothing ruling them out. They're even real. That just don't have a Lorentzian continuation, and it's currently unknown what to make of them. Or if you want, I can rephrase the question. In QFT, What is the partition function of a superconformal field theory on S3? What's its interpretation in Lorentzian? If I had a thermal circle, then I can make it in a trace. But that's not true for S3. Perhaps the solution to this is in the fact that we should be more relaxed about our reality conditions, as James was saying earlier, in the sense that the saddle points, when you do a saddle point approximation, can also lie outside the contour that you had decided to start with to begin with. So perhaps we should include complex solutions for which everything I said is not true. The Lorentzian, meaning real Lorentzian, requires this vector field, but I can define a complex metric on S3 that has a negative signature. That's the end of the issue. Questions? Okay, good. So, other issue, which is a little bit more well-defined, in the sense that it's clear why it goes wrong, is the conformal factor problem. This had been found. These are issues that were pointed out immediately, in the first couple of years. Yeah. Yes.
So my point is that can we possibly explore into the process just which means Lorentzian so you read it but not over all the proposals, but only over those which do
Perhaps that's the correct prescription. I don't know. Perhaps that's true. However, the rotation, the black hole is not really neither Euclidean nor Lorentzian, right? I had to do analytic continuation between them in order to make it work. Yeah. So but yeah, it's a topology that admits a Lorentzian metric in principle. It's not the one that you use to do the computation. Perhaps that's the correct approach. One thing that is known is that in 2 dimensions, you also have to include wormholes. So disconnected boundaries too. That's one thing that recent work has shown. Okay, so the conformal factor. Many people asked me about this, so it's already known in the audience. But we did the Wick rotation to make to say that the hyperbolic became elliptic, but also arguing that the path integral in this form had a better hope of converging because the on-shell action was real and had a minus sign. This is true for spin 0, 1/2, oops, and 1 particles. Sorry, spin 0, particles. Meaning it's true for their action, for the Maxwell action, Dirac, and Klein-Gordon. It's not true for gravity, because let's take the Euclidean action of gravity. I'll do it with 0 cosmological constant. M dm. Now, in principle, just like I integrate over GE and H, let's just call them G and H, I should also integrate over the ones that are conformally related. So I should integrate over the G star, G tilde, that are conformally related by an omega. This is not a diffeomorphism, it's really a change in the space of metric. So it's not something that changes one solution. However, under a conformal rescaling, both the Ricci scalar and the extrinsic curvature change and when I substitute it back, I'll find that the on-shell action on G tilde is equal to minus 1 over 16G over M of omega squared R plus 6 Why is this a problem? Because I can make it as for the one metric, I can make it as negative as I want. So the on-shell action is unbounded below. Therefore, the path integral is not convergent. However, at semi-classical level, only at one loop. Because it's not, at semi-classical level, so everything that we've done until now, we have only considered one solution, and I said that this is not a diffeomorphism, so it's not a change of coordinate for that solution. It's really a change in the space of metrics. There are various suggested ways of avoiding the conformal factor problem. The latest I know, it's a paper in May that stated that the Euclidean contour is just without hope. There's no way of avoiding the conformal factor problem. So we should be more inventive. This is a paper by Santos, Horowitz, and sorry, a quote. Marulf? Probably done. Yes. Yes?
This transformation is not diffeomorphism. Then why do we want to perform this transformation? Why is it relevant?
Because I should integrate over the space of all metrics, not just one metric and all the change of coordinates. Yes. In principle, you should say, I take one topology and I integrate over all the metrics that live on that topology. This is the same topology, it's just a conformal rescaling, and I've screwed up my action. I can conformally rescale it to anything I want, and the action will divert. And the problem is that it's a Ricci scale. It's a Ricci scale, the crucial bit, while also the Gibbons-Oaking bit. Yes?
Maybe it would be like a comment. Because here you can just first power of the Ricci scalar, but we know that if in principle we can make it quadratic, then it would behave better. So of course I can here advertise conformal gravity when it states that there's a square of the right tensor, and when I think this problem there doesn't appear. I mean it's
Yes.
Although of course conformal gravity is other problem, but at least this would be solved, I think.
Yes, sorry, I was here I was only restricting myself to Einstein-Hilbert, but of course another way of solving all these, some of these issues, or trying to solve all these issues, is to consider different theories of gravity, or conformal, Lovelock, whatever you want, F of R, and and consider what is the. But then the difficulty with all these theories is that you also need to make sure that the initial value problem is well defined, which for the Einstein-Hilbert is all solved. And
That's the idea, because
yes.
we have this problem, but it was quadratic.
Yeah, so it's in a sense a little bit like like the blanket. You move the blanket a little bit to solve one problem, but then the feet are cold. It's yeah. The true statement is that we don't know how to quantize gravity. But this is a good framework. I should stress that even with all these issues, the first 6 hours, the first 4 hours and a half were good. they work. So it's a good framework. Okay, last issue, I'll finish in a little bit early, and we can go for lunch, is the gauge group, is the fact that gravity is really a redundant theory, includes a redundancy, as it was also mentioned just now, is the fact that I should also include the fact that I can change the coordinates, and this is a gauge redundancy in the sense that it's the same solution that I'm talking about. So it's a redundancy in my description. There are various ways of dealing with gauge redundancies in quantum field theory, BRST, BV, ghosts, anything that you want. This is not been solved for gravity. One of the issues, there are various issues. One of the issues is that the gauge group is the infinite dimensional space of the diffeomorphisms of my space, the connected component to the identity, sorry, component connected to the identity of the diffeomorphism of this is infinite dimensional, generically. Why? Okay, so let me justify why this is the case. So, first, let's argue why there could be multiple components, multiple connected components for the diffeomorphism group. Take a Lie group. Then the Lie group acts on itself via diffeomorphisms, via left product, right product, whatever you want to call it. Therefore, the diffeomorphism group contains G itself, but G could be could be disconnected, could have multiple components. So generically, this is the case. The statement is that the other components that are not connected to the identity are really acting non-trivially. They're not gauge redundancies. They tell you something about the fact that you're changing the solution. However, it's not even fully true what I said until now, because I should only consider the small gauge, the small diffeomorphisms. What does this mean? Suppose I have a diffeomorphism in the component connected to the identity that is generated by a vector field X. This is the first and last time that a vector field will be X. But so X generates an element in diff 0M. Sorry. And let it act on the Lagrangian density, which is R minus 2 lambda square root of G d for X. It acts on the Lagrangian via Lie derivative, and its action, if you're careful about the fact that you have the volume element, which is a tensor density, not a tensor. Okay, let's be more formal. This is the volume. So the volume is the formal, but it's well, okay. You know how it works. At the end of the day, you'll find that this is the case. Sorry. Therefore, this is really a boundary term. So the variation induced on the Lagrange, on the action, is really a boundary term. However, if the vector field doesn't have compact support, or the vector field doesn't vanish sufficiently fast at infinity, then this variation will be non-zero. These are interpreted as a non-trivial action on the theory. That is, it's not gauge. It's not a redundancy. So the problem is what happened at the boundary of my space. But this is something that you could have you could have thought of, because it's always a problem with the boundary, because as we saw, there is ADS-CFT, that is that gravity in ADS is defined by my boundary, and if I have an action on the boundary, then it changes my theory at the boundary, and therefore it changes the gravity that I'm working with in the bulk. You can make everything that I said now in a wishy-washy way, in this action on the boundary, if you do the Hamiltonian description. So in the Hamiltonian description, we take a Lorentzian space that is also globally hyperbolic, in the sense that there exists a Cauchy surface whose future domain of dependence, so everywhere in space that is influenced by what happens on the Cauchy surface, is the entire space-time, future and past, of course. This guarantees that if I solve, if I have initial data on the Cauchy surface, then I can solve the hyperbolic differential equation everywhere on space-time. These particular type of spaces have what is called a time function, that is T, that is globally defined, such that the topology of the space is of this form, is RT times sigma, where sigma is some 3-dimensional or d-1 dimensional space, and the metric can always be written in this way. This n is sometimes called the lapse function. These ni are called the shift vectors. And this is the induced metric on sigma at a fixed time t. Right? And xi, xj are the coordinates on sigma t. Sigma. Okay? This is sometimes called the ADM decomposition, or the 3+1 decomposition. And it allows you to define, t is not necessarily an adapted coordinate. It's not, dt is not necessarily a killing vector. It doesn't have to be an isometry. So this can depend on t, this can depend on t, this can depend on t. There is a special class of global hyperbolic spaces where it's stationary, and then t is an isometry everywhere. Now I can construct a symplectic-like formulation of GR, so I can construct an Hamiltonian formulation of GR. So I define the initial value problem. Is given in terms of n, ni, and hij. These are the canonical positions. In a sense. And you can construct the canonically conjugate momenta. By taking the derivative of the Lagrangian with respect to the derivative of the canonical position. In particular, there is one that's particularly interesting for us. That is the canonically conjugate momentum to the induced metric on the hypersurface, which turns out to be pi ij, where pi ij is kij minus khij, or plus, minus, which is the Brown-York stress energy tensor. And, oops, disappeared. Okay. And the Hamiltonian that you construct once you do the Legendre transform with this canonically conjugate momenta is composed out of a bulk term plus a boundary term which is proportional to the integral of pi ij. And the equations of motion are such that this vanishes on shell. So really, the Hamiltonian of GR is a boundary Hamiltonian. This is all consistent with what I said now, so that I should only consider small diffeomorphisms, the ones in the component connected to the identity that don't act on my boundary. Because otherwise, I'm really changing the theory. I'm changing the Hamiltonian of my theory, which is all consistent with ADS-CFT. Fun fact, the Brown-York stress energy tensor is really the stress energy tensor of this formulation, in the sense that if you vary the metric delta Hij, then you really get the Brown-York stress energy tensor. Okay, questions about this? Okay, if not, I hope I have convinced you that black holes are fun, that we know some things about them, but there is plenty that we don't know, so you should all work on them. In particular, there is a good framework to understand quantum gravity, to understand quantum effects in gravity, which is given by the gravitational path integral, even despite all the issues that I talked about today. Thanks.
Thanks again for the lectures, Pietro. Thanks for agreeing to give them. They were great. Are there any questions?
In the gravitational path integral, you're doing the calculations in a set of perturbative approach. So how can we include, I mean, for the quantum black hole, I guess the non-perturbative effects like instantons or other non-perturbative effects could contribute for the quantum black hole. How do you incorporate these effects in the set?
Yes, so thanks. It's a good question. And so there is one thing that I should have perhaps stressed more, is the fact that when I do, if you assume that you're doing the path integral in the same way that you would do the path integral for a field theory, if you consider a black hole, that's already a non-perturbative effect. Because it's another saddle. Usually, we take the vacuum gauge field, the gauge field configuration that is trivial, and we do the quantization around that, and we say, these are perturbations around the vacuum, and then you consider an instanton, so a non-trivial configuration with star f is equal to f, something like that, and you do perturbation around that vacuum, you consider the zero mode, or something that, whatever you want to do around that instantons. Here we are considering different saddles, so we are doing non-perturbative effects from the gravitational path integral viewpoint. You could worry about the perturbative effects around each saddle. You should worry about the perturbative effects around each saddle. These are the one loop contributions that I mentioned earlier. Without supersymmetry, I don't know of any method to attack them. With supersymmetry, in very special configurations, such as with a lot of symmetry, such as near horizon geometries of black holes, ADS2 times S2, for instance, and a lot of supersymmetry, then there is the possibility of computing the path integral exactly from gravity, in the sense that you can take into account all the perturbative effects around each saddle and sum over the saddles. But that's really a cheating thing, because what you're doing is that you're reducing the path integral on ADS2, and then you're doing two-dimensional gravity, so you're considering it's a great result, but it would be nice to extend it to non-near horizon geometries. There are other non-perturbative effects. I considered only one black hole, but there are multiple black hole configurations as well. Yeah.
And if you have the Hamiltonian for gravity is only on the boundary, can you say this is another evidence for, I don't know, holographical principle like ADS-FP?
Yeah, for sure.
Maybe it will be follow-up to the previous question. So, I mean, in the general formulation for the GPI, we have to integrate over all metrics. But if we, for example, use this symmetry-reduced version that we want to preserve, like you said, if we take ADS2 times S2, we do not allow for the fluctuation of ADS2 structure. And yeah, do you think that generally this can help if instead of integrating over all the spaces of metric, that basically is infinite dimensional and we cannot classify, so we are talking about the things which mathematically do not exist. So instead of doing this, is it possible that just integrating over some reduced variables which are not allowed to fluctuate, whether this could help, or whether there is any hope that this could help?
Yes, there is definitely hope that this could help. It's not a hopeless endeavor. So there are various things that one could tell you. So the first thing is that it's sum over metrics and topologies, right? So in 2 dimensions, this is relatively under control. There is a theory of 2-dimensional gravity in ADS2. They do the sum over topologies and they recover the behavior that they would expect from the 1-dimensional dual, like a plateau and instances of chaos. In higher dimension, this is not known. Perhaps in 3, some things are known. There are corrections to. Anyway, in 4 dimensions, I am biased by working with my collaborators, but I think that the biggest hint that such a thing should exist, so a restriction to a certain set of configuration and integration over that exists, is the fact that you can do supersymmetric localization on the path integral in the dual superconformal field theory in any dimension. So if I tell you, these things would have been nicer said without the recording, but if you believe that ADS-CFT is this, not Sucra, sorry, quantum gravity equals to the superconformal field theory, and you can compute this, because there is a way of computing the superconformal partition function only taking contribution from protected sectors. So as you said, reducing the path integral, which is infinite dimensional, to a finite dimensional integral over some gauge field configurations or matrix model of sort. Then perhaps the same thing can be said here. There is a subset of all the infinite dimensional fluctuation that is perhaps protected by supersymmetry, perhaps protected by something else that contributes to this. So far, what we've showed is that at the semi-classical level, there is, so supersymmetric semi-classical level, there is in fact a further restriction, so not the entire spacetime contributes, but only the fixed points of these symmetries. There are other approaches that you can take to this. So there are protected subsectors of this equivalence that are supposed to be captured exactly. So for certain superconformal field theories, there exists a subsector of all the operators that are protected by some subalgebra. And you can twist the theory of quantum gravity that you can think that you can work with. And you can show that the right configuration with the appropriate holographic boundary condition reproduces the same correlation functions between the operators in the protected subalgebra. This is really, research that has been, it's really current research.
Okay, thank you.
All right, so maybe let's call it at that, and you can keep on discussing during the poster session that starts at 2. Let's thank the speaker again.
Thank you. And the